Hi everyone, today is fun maths. 2 plus 2 equals to 5. Oh, what's this again? Today we are talking about inertia. What is inertia?
Hi everyone, today we'll be talking about simple pendulum. In our last video, we talked about mass spring system and everything that is related to it. Today we'll be talking about simple pendulum and everything that is related to it. Simple pendulum is set up in such a way that we have a string that is being attached to a fixed place, and we attach a bulb to it. So we attach it to it, and then we give it a slight displacement, say to this side. Now if you give it a slight displacement, this will have angular displacement. Now here we are not talking about linear displacement. Here we talked about linear displacement in mass spring system. Here we are dealing with angular displacement, theta. And if you should leave it, remember it will move in an arc and go back to this place and go back, and it will come back to this place and going back and forth. And don't forget that this angle here, which is theta, is equals to this angle here, theta, and that theta must be less than or equals to 10 degree. Any angle greater than that is no longer simple harmonic motion, because if you displace it more than 10 degree, then you will get varies period. So in order to get a constant v period, then we displace it any angle less than 10 degree. Now we know that as we drag it to this side, we give it this, there is a certain force that will be opposing the force at which we use it to push it to this other edge here, and that force is what we call restoring force, and that is what simple harmonic motion is always talking about. It's talking about the restoring force on an object. And don't forget, this restoring force is always perpendicular to this length, the length of this string. The restoring force is always perpendicular to it. Let's know that. And if I should come to this other side and then analyze all the forces that is associated to this string, remember we have the length of the string, we have the angle theta, and there is a restoring force that is acting like this. All the forces that is acting on this, we have the weight of that object that is acting downward. Weight acts that vertically downward. And if I should duplicate the force that is here, because there is a force here we call the tension in this string. If I should duplicate it and bring it to this side, this is now parallel to this. And mind you, that's how we resolve any vector component. If we have two vectors like this, if one is going like this, one is going like this, we can say that this horizontal one can be resolved like this, and this one can be resolved like this, and then we can now use it to resolve and calculate our answer. And the logic there is that they must be perpendicular to each other, parallel rather, they must be parallel to each other. As you can see, this is parallel to this. Now if you now want to talk about this angle, we can see that this one also is vertically downward, like this our weight mg. Our weight here also is vertically downward. Then the angle theta here is found in between the vertically downward weight and the slant length, which is the tension that is inside this one. Let me put this one as T, the tension that is inside this one. So the angle is in between the vertical weight and the tension, which is this tension and this vertical weight. Then the angle is in between here. And don't forget that between this vertical length and this restoring force is 90 degrees. So this is the restoring force and the vertical length is 90 degrees. Boom, we have our right angle triangle. And we know if we have a right angle triangle, the place facing the 90 degree is the hypotenuse, where the place facing the angle we are looking for or we are considering is our opposite, and other side is the adjacent. And if we are resolving this, we resolve it in sine theta, and sine theta equals to opposite over hypotenuse. Our opposite here is our restoring force, so our restoring force over hypotenuse is our mg. Then we can say our restoring force equals to sine mg sine theta, mg sine theta. And likewise here also we still have a tension which is in our cos theta. So cos theta is tension over mg weight, and then we should cross multiply. We have the tension to be equals to mg cos theta, mg cos theta. Now if you should look at this scene very well, we see that it's like a circle, something like this, a circle, and a bulb is rolling like this, back and forth in just an arc of this circle. Now remember that if it is a circle that we can if it is in a circle like this and we are having a tension like this, there must be an opposing force which we call centrifugal force, and this centrifugal force is actually equals to the tension in this string. Since they are equal, if we are considering all the forces that this one we have, we know that both of them will cancel out because they are opposite to each other and they will cancel out. Then the tension in this string is not considered for these equations. Then I rub that one off. Now the restoring force is now equals to the force at which I used to pull it, and you know this force I used to pull it is ma. The sum of the algebraic sum of every forces is ma, which is equals to negative mg sine theta, because remember the force I'm using to pull in it is like this, towards like this. Then they are opposite to each other, then they must be equals to each other. Since they are equals to each other, the restoring force tending going backward will have a negative sign, and then I can divide both sides by mass. Our acceleration will be negative g sine theta. Now in this acceleration, now I can now relate it to our angular displacement. Remember, our acceleration is the second derivation of displacement and time. That is our angular, that is our acceleration. Now how do we visualize this displacement that we are talking about? Now if you should look at this setup very well, it's an arc like this, and the displacement we are talking about is this length of the arc, and this is the displacement, this is the length. Then we can see that, okay, as we know that the length of an arc is equals to theta over 360 times 2 pi r, and our r is radius. Now the length of an arc is this s, so we can say our s equals to theta over 360 is 2 pi in radian, because we are working in radian here, times 2 pi. Our r radius is this length, remember, is the one that goes round a circle like that, so that is our length. Then 2 pi cancel 2 pi, our s will be equals to l theta. But what I need is not s, what I need is the acceleration, but acceleration is the second derivation of this with time. Okay, and we know that our theta also is a function of time, since when we leave it, the displacement decreases with time. So we can say our s, which is equals to l theta. If you should differentiate it at first, we have s dot, which is equals to l theta dot. We are differentiating a function with respect to another function, you divide it by that function. For instance, if we have y equals to 7x and we are differentiating with respect to t, we say we have the y dt to be equals to 7 the x dt. That's how it works. And if you should go again, we have the 2y over the t square equals to 7 the 2x over the t square. That's how we solve that. Likewise, if you are differentiating with respect to x, that's how it works. Differentiate y, we have the y over the x, because we are differentiating with respect to x. 7 differentiate x, we have the x over the x, and the x over the x is 1. That's why we have only 7 if we are differentiating. The differentiating this will give us s dot dot to be equals to l theta dot dot, and since we have l theta dot dot, I can represent my acceleration with this, and we say that our acceleration is l dot dot theta. L theta dot dot equals to minus g sine theta. Dividing both side by l, we have theta dot dot equals to negative g over l sine theta. Alright, now this is where the assumption comes in. Now, solving with sine theta is all rooted. If you are going to put it inside our equation, it's going to be complicated. Now, how can we resolve that? Now, that is when an assumption of theta must be less than equals to 10 degree, because sine theta, as theta tends towards 0, the sine theta tends to also. You can see that also in Taylor series when a approximated sine as theta minus theta cube over 3 plus theta raised to power 5 over 5 minus dot dot dot, like that. So you approximated it. So as theta tends to 0, we can just say our sine theta is approximately theta. And you can try it. Take your calculator, put it on radian and check. 10 degree is it's approximately equals to 0.05 radian. This is how you do. 180 degree is equals to 1 radian. Then we can say that our 10 degree is equals to how many radian? Cross multiplying, we have x times 180 degree equals to 10 degree radian. And if you should divide by 180 degree, then we see that our x equals to 0.0555 and approximately 0.56. And if you should punch this inside calculator, sine 0.01, you will get 0.01 or approximately 0.01. Sine 0.02, you get approximately sine 0.02. Sine 0.05, you get 0.05 back. So we can now assume that as theta approaches is getting smaller, this is sine theta is approximately theta. Then we can just change this to theta, since we know that the assumption for simple pendulum is theta must be less than equal or equals to 10 degree. Then we can say theta degree equals to negative g over l theta. Alright, now this is one formula also. Let's put it at the side. Moving on, we know that our theta is a function of time, and we say that it's a sinusoidal function, because if you check it, we see that it's a sinusoidal function, and that's why we call simple harmonic harmonic, because it's a sinusoidal function. Now we can just say this is equals to, our amplitude here will become our maximum displacement, which is maximum angular displacement times cos omega t. I think we explained it in mass spring system. Now differentiating this, now if you are differentiating cos omega t, this omega t is what is the first thing you are differentiating. Remember, theta max is constant, it doesn't change. So if I'm differentiating this, the first derivative, this theta max is constant, and differentiating omega t with respect to t, you have omega, and differentiating cos, you have negative sine, and you put this omega t back. And if you should open these brackets, you have negative omega maximum angular displacement sine omega t, and that is right for our differentiating it once more, because we need the second derivative, and the second derivative is going to be something somehow the same, because this is constant. Differentiate this, you have omega, and differentiate sine, you have cos omega t. Opening the brackets, you have your second derivative to be minus omega squared, because this omega multiply this omega, you have theta to be max, and you have your cos omega t. And don't forget that our cos omega t is actually equals to our theta, because this is omega maximum amplitude times omega t. Then we can just represent this one as our theta, and then we say our second derivative equals to minus omega square theta. And if you should relate this to this, because they are looking the same, we can actually see that our omega square is equals to g over l, and that implies that our omega is equals to square root of g over l. But mind you, we say it is approximately equals to square root of g over l because we approximated this function. So we can just say we know that our omega is equals to 2 pi over t, which is t for period, not tension this time around, t for period. By the time we find our period, t will be equals to 2 pi over omega, and our omega is actually equals to square root of g over l from this place. Then we can say t equals to 2 pi over square root of g over l. Let's simplify this. T equals to 2 pi divided by square root of g over l, and we know that when we change this division to times, then we flip this, then we have l over g, and our tension will be equals to 2 pi square root of l over g. Then I can just put that at this right corner. That's our frequency. Our frequency is equals to 1 over period, and since our frequency is 1 over period, we are going to reverse everything that is here, which is 1 over 2 pi and square root of g over l, and that is for. If you look at this equation very well, or those equation very well, you can see that our angular frequency, it actually depends on only gravity and our length. Likewise, period and frequency, they depend on only gravity and length. And we can see from here that our length is the string is inextensible, it doesn't extend, so there is no change in length, there is no increase in length. Therefore, our angular frequency is always constant. But our, because it's having a torque, it rotates, and as it rotates, it changes with torque. Our torque and the torque of this guy changes, so it doesn't have angular momentum, unlike a circular motion whereby we don't have any torque and there is angular there is constant or in angular momentum. So every other thing in this place is not constant except for angular frequency. Thing very well. Now, if I have a bulb like this and it's like this and it's moved back and forth to this place, at this particular place our velocity is 0, and don't forget that place we have our theta to be theta max. Our angular displacement is always maximum, and our potential energy also is maximum there. So that one will also carry us to potential energy. And here also our t is maximum, whereby our theta is 0 because there is no change in this, so our potential energy is 0. Kinetic energy here is also 0, and total energy here is equals to our potential energy. And here our kinetic energy here is maximum, and our total energy is equals to our kinetic energy. And at this point our velocity is 0 because it's not moving. Here it's 0, then it's moved like this. As it move like this, the velocity starts increasing 1 2 3 4 5 6 7 8, and once it gets to the middle it becomes maximum, say 10. And if you are moving backward like this, then it reduces back 9 8 7 6 5 4 3 2 1 0, and continues like that. It comes back again, it's increase and decrease, and that is how it goes back and forth. And here, so our theta here also is maximum, and our potential energy also is maximum here. Our kinetic energy is 0, and our total energy is equals to our potential energy. We are going to use this logic when we are deriving for total energy. Now let's first talk about our potential energy. potential energy is mgh in this scene because gravity is acting upon it. But here, what is our h? We are having length of an object. Now let's analyze what our h is. Remember, this is how the thing is being set up and it's moved this way. Now we have the length of the bulb here, and don't forget, from ear to ear, from this top to this bottom, is the length of the bulb also. Now this place, from this place, is the height we are talking about because it's moved from this place and it goes up. Do you remember that your potential energy doesn't depend on the path take, it just depends on the height, how high is the thing. So the potential energy is from ear to ear. The height is from ear to ear, from this point to this point. But from this point to this point is what we don't know. So let's call it x. From our logic, we know that this place is our theta. Drawing a vertical line here makes this place perpendicular and makes this place our hypotenuse. And if this place is our hypotenuse, then we know that here is our opposite and here is our adjacent. Then what is related with this place and this place? We know that our cos theta, because it is adjacent we are talking about, is adjacent, which is the place we are looking for, over hypotenuse, which is our length. If we cross multiply, we have our x to be equals to cos theta, L cos theta. Don't forget, is this height we are looking for, so that we can replace it here. And you know that this height actually plus this x is equals to the length of this rod. Now we have known our x to be L cos theta, then we can just say our height plus L cos theta is equals to L, and then our height is equals to length minus, if I should bring this to the other side, it becomes L minus L cos theta. Then we can say that our height is probably L into brackets 1 minus cos theta. Then let me replace it here. Potential energy will now be equals to mg L minus g L minus L into brackets 1 minus cos theta. Now here also, you see we are having cos theta. We have to assume, as we made an assumption for sine also. From Taylor series also, we know that cos theta equals to 1 minus theta squared over 2 plus theta raised to 4 over 4 plus blah blah 4 factorial rather. Then we are just considering only just this, because this is very small. Then we take which we can use to represent it, which is just this first two. Then if we should put it inside this, we have our potential energy equals to mgl 1 minus theta square over 2, which is this guy here. Opening up the brackets, we have our potential energy to be equals to mgl. We have 1 minus 1 plus theta squared over 2, and 1 minus 1 cancel out, and we have our potential energy to be equals to mgl theta squared over 2, or we say our potential energy is equals to 1 over 2 mgl theta squared. But we can represent this g as omega square L, since it is related in this place. Then I can just say our potential energy is also equals to 1 over 2 m. Our g become omega square L. Then our length, we multiply this length, we giving it length square theta square. Then we can say this is our potential. This is also part of our potential. So let me put our potential energy at this corner. Moving to kinetic energy, we know that our kinetic energy is half mv squared, but we don't have our velocity. We don't know what our velocity is, but then we can come back here. We know that our velocity is the s over the t. Okay, we can now say that we can use our s equals to L theta. If we should differentiate these ones, we have our velocity, which is equals to L differentiate this theta once. Then if I should represent this with this, I will have my velocity, which it will be L theta. The L, the first differential of theta. And then we can now say that our theta, since our theta is this, then I can say that my V, which is my velocity, is equals to L multiplying minus omega theta max sine omega t. If I should bring it here, we have V equals to L minus omega theta sine, but that is our maximum angular displacement, omega t. And then we can open up the bracket saying V equals to minus omega L theta max sine omega t. This omega sine t is not what we have from the beginning of the equation. We know that we have theta equals to theta max cos omega t. Then how can we change this? Remember our trig function, sine x plus cos square x is equals to 1. Then our sine x should be equals to square root of 1 minus cos square x. Replacing it in this one, I can say V equals to minus omega L theta max square root of 1 minus cos square omega t. Now I can bring this theta max into the square root, and I will have V to be equals to minus omega L square root of omega max squared into brackets 1 minus cos square omega t. And then we say V equals to minus omega L square root of omega square max. If we open the bracket up, we have minus omega square max cos omega t. Replacing this with my theta that I have left, so I will say V equals to minus omega L square root of theta square max minus, since both of them are carrying square, then I will have theta square also. Then this is my velocity at any point. Lastly, analyzing our total energy. We know our total energy at any point in this system is kinetic energy plus our potential energy. Then our kinetic energy is half mv squared, and our potential energy is half m omega squared L squared theta squared. Alright, now adding this together, changing this v squared to this that we have here, we can say we have half m minus omega L square root of theta squared max, theta max squared minus theta squared all squared plus half m omega squared L squared theta squared. And opening up the brackets, we have our total energy to be equals to 1 over 2 m omega square. Omega square will give us omega square, minus times minus will give us plus, so we don't need that. So L square will give us L square, and this square root we cancel square root, so we have theta max squared minus theta squared plus half m omega squared L squared theta squared. Having this now, I can just open up these brackets. The total energy to be equals to half m omega square L squared times max omega square minus half m omega squared L squared theta squared plus half m omega squared L squared theta squared. What I did here was to just open this bracket. I use this to multiply this, so I have this. I use this to multiply this, I have this, and this is this. That's all that I did. Now analyzing this is negative, this is positive, they can cancel out. Then our total energy is now 1 over 2 m omega squared L squared maximum amplitude. And if we should test this in any area, we will know that this total energy is constant, and make sure you know that total energy also is constant at any point, is the same, and is equals to potential energy plus kinetic energy. This is all we need to know about simple pendulum. If you like this video, hit the like button, subscribe, and share it